Question number 1. If a magnet is dropped into a coil of wire connected in a closed circuit, it will fall with an acceleration equal to g more than g less than g or equal to 0. Now, this goes along with the electromagnetic induction. Whenever you have a coil connected to a galvanometer in order to complete the circuit, so like this, and if you move a magnet towards or away from the coil, then the magnetic flux linked with the coil goes on changing as the magnet moves towards the coil or away from the coil. That change in flux induces an EMF, and that induces a current also. When that current flows to the coil, there is a current in the coil which produces a magnetic field because of coil also, because of current also. Now, according to Lenz's law, this current should flow, that is induced current should flow in the coil in such a way that it should oppose the cause. Here cause is the motion of the magnet. So when the induced current flows in such a way as to oppose the motion of the magnet, this coil having the induced current turns to be, this phase turns to be the north pole. So if this magnet is moving towards, this happens to be the north pole of the coil, and this north pole opposes this north pole motion towards it. So automatically the acceleration due to gravity of this magnet should decrease because of this opposition. So this is less than z. Option is C. Question number 2. A small inductor coil of inductance L is cut into two equal parts and both are connected in parallel. The net inductance is. Now we have to work with the formula for self-inductance. Suppose you have a coil of many turns like this, and if L is the length of the coil, and the self-inductance of this coil is given by mu naught n square EAL, where A is the area of cross-section of the coil, this area of cross-section here, and L is the length of the coil, and N is the number of turns per unit length. Be careful about the small n. It is not the total number of turns, it is the number of turns per unit length of the coil. Now, when the coil is cut into two equal halves at this, by cutting it at the center, N doesn't change. Why? Because suppose this is a coil of length 100 centimeters, say, having 100 turns, total number of turns 100. Now the number of turns per centimeter will be 100 number of turns in 100 centimeter. So it is 1 centimeter, 1 turn per centimeter. That is N. Suppose you cut it into two equal halves, the new number of turns will be 50 centimeter, or 50 turns will be found in 50 centimeter. So total will be one turn per centimeter itself. So N didn't change. So number of turns per unit length remains the same even if the coil cut into two equal halves. So in the formula, mu naught is a constant, N is a constant, and when the coil is cut into two equal halves, area doesn't change, area of cross section. So L has to be linked with the length of the coil only. So length of the coil is halved, so automatically the self-inductance will be halved. So now you have two coils, small pieces, and they have to be connected in parallel after splitting them into two. So you have two coils of self-inductance L by 2 connected in parallel. L by 2 because of making the length into two halves, halving the length, and so self-inductance gets halved. And now just use the formula of resistances in parallel, R1 R2 by R1 plus R2. So that holds good for inductors also. So equivalent value of self-inductance is L by 2 into L by 2 divided by L by 2 plus L by 2, R1 R2 by R1 plus R2. That is equal to L square by 4 divided by half L plus half L. That is equal to L by 4. So option is C, L by 4. Problem number 3. An aeroplane having a wingspan of 35 meters flies due north at a speed of 120 meters per second. If the vertical component of Earth's magnetic field is equal to 3 into 10 to the power minus 5 Tesla, the potential difference between the tips of the wing will be. And you see all the answers options here. All the digits are same, but only the decimal point varies from option to option. That's all. So how to work out problems of this type? Now this is a problem related to induced EMF. We know that whenever a rod moves in a magnetic field, when it cuts the normal magnetic field lines, an EMF is induced in the rod. Suppose this is the rod, and if the magnetic field lines are normal to the plane of the paper like this, and as the rod moves like this, and an EMF is induced, B is equal to, sorry, induced EMF is equal to BLV. Now, how can you apply the same concept here for the aeroplane? Now, aeroplane, when it moves, it cuts the magnetic field lines. The wings of the aeroplane may be assumed to be made up of metal, and as it cuts the magnetic field lines, an EMF is induced on the tips. Now, which magnetic field line is going to cut now? It is the Earth's magnetic field lines. We know that Earth behaves like a magnet and it has a magnetic field. Suppose this is the surface of the Earth, and Earth's magnetic field will be neither parallel and nor horizontal. But you can take the component of Earth's magnetic field along the vertical and along the horizontal. And when an aeroplane moves like this, it is the wings of the aeroplane which cut these vertical magnetic field lines. So when these wings of the airplane cut the vertical magnetic field lines, it is very similar to a rod moving in a magnetic field. You can use the same formula for induced EMF. So if you apply E is equal to BLV, then induced EMF is equal to B, strength of the magnetic field, that is the vertical component of the Earth's magnetic field, it is given 3 into 10 to the power minus 5 Tesla, and length of the rod is nothing but the length of the wings of the aeroplane, that is 35, and V, velocity is 120 meters per second, and this answer is supposed to be, now 3 into 35 gives 105. It is 3 5s are 15, 3 3s are 9, and I will take it as almost 100 because I have all the answers similar. So answer should be 126. Now 3 into 35 is almost taken as 100 into 120 into 10 to the power minus 5. That's what I will do. Now E is almost equal to 100, 1 into 12 is 12, and here you have 1 0, here we have 2 zeros, so totally 3 zeros, and into 10 to the power minus 5. Now if you bring 10 to the power minus 5 here, 1 2 3 4 5, it is 0.12 volt, and the nearest answer is 0.126 volt, that is option B. So this is the way in which you can work out the numerical problems when the answers are very similar except the decimal points. And if you have any other idea, you can use also, and so option is B, 0.126 volt. Problem number 4. A metal rod of length 2 meter is rotating with an angular velocity of 100 radian per second in a plane perpendicular to a uniform magnetic field of 0.3 Tesla. The potential difference between the ends of the rod is. This problem is based on motional EMF itself, but the type in which the rod moves is little different. We will visualize this in a diagram. The rod is rotating in a circular path, and suppose imagine that the magnetic field exists but normal to the plane of the paper like this, and imagine a circular frame kept in the magnetic field like this, and now our iron rod is placed with this one end here and another end touching the frame like this here, and now this moves in this direction with an angular velocity omega. Now, when it moves like this, angular velocity for the rod will be same for all the points of the rod. Suppose imagine that this rod is divided into a number of parts, and consider a small piece here whose thickness is dx, and let it lie at a distance x from the center of the rod. And if you observe the formula to be used here, induced EMF, we know when a rod moves in a magnetic field, induced EMF is BLV. But the problem here is magnetic field is same everywhere and it is normal to the plane of the paper going into the paper, and length of the rod doesn't change, and V is different for different pieces of the rod. A piece taken here will have some velocity, and a piece taken here will have the maximum velocity, and a piece taken here will have the velocity 0. So how can you substitute V common for all the whole length of the rod? It's not possible. So we have to go for some other way. So that's why we have considered a small piece of the rod which is lying at a distance x from the origin O or the center O. Now For this piece of the rod, we can write velocity as V equal to R omega. I will try to bring omega as far as possible. The reason is omega is same for all the parts of the rod. Suppose this part of the rod turns by an angle 30 degree, this will also turn by an 30 degree because this is a solid rod and it says yeah, all the pieces of the rod will be moving by the same angle. So when this moves by 30, this will also move by 30. So omega is same because we define omega as the angular velocity, angle covered by time taken. So d theta by dt is same for all. So let us try to bring omega as far as possible in the formula. So for this piece of the rod, if I want to write the induced EMF formula, E is equal to B is same for all the pieces of the rod, but length of the piece that I have taken, element that I have taken here is dx, and V I can replace it as R omega. R is x for this piece, x omega. So this is taken from this formula. So for V, it is x omega. Now, what is that? And I will take it as a small EMF induced for this element only. It is not the full EMF. For full EMF induced in the whole rod as it cuts the magnetic fields introduced here is given by integration of small such EMFs starting from the 0th piece, which is lying at the O center, up to the full length L. Such pieces have to be taken from starting 0 up to the full length L. So 0 to L is equal to integration from 0 to L P, and I'll write omega and x dx. I'll write B and omega are constants, need not be brought under integration. Only x has to be integrated. So induced EMF E is equal to B omega. I'll write the integration of x as x squared by 2, and the limits are from 0 to L, and this will give you B omega L squared by 2. This is the induced EMF, and if you want to get the answer, E is equal to, and here if you want to change the formula as in terms of velocity, of course here it is given angular velocity itself. I will finish it here only. If you want to put the formula in terms of velocity, then omega can be written as V by R. Here full R is L, so omega V by R. Omega is V by L by 2 again into L square, and this comes to 1 L will get cancelled, B V and L by 2. But here of course we can use this formula itself because we are given with the angular velocity. So induced EMF is B is 0.3 Tesla, omega is 100 radians per second, and L square length of the rod, that is 2 squared 4 by 2. 2 gets cancelled, and here 2 times. This is 0.6, 2 into 0.3 is 0.6, 0.6 into 100 is 60, so it is 60 volt, option C. Problem 5. The amount of charge flowing through a 10 ohm coil when the magnetic flux linked with the coil changes from 0.75 Weber to 0.25 Weber in 0.1 seconds is. Now, the change in the flux is given, time is given, so you can find out induced EMF. Once you get the induced EMF, you can find out what is the current, because you can apply Ohm's law, E is equal to V by R. Once you get the current, you can find out what is the charge flowing into the circuit. So you have to go in a reverse way. First of all, we will find out what is induced EMF. According to Faraday's law, E is equal to d phi by dt. I will use only the magnitude. Induced EMF is equal to d phi by dt. And that can be solved as the change in the flux is 0.75 Weber minus 0.25 Weber divided by, and that happens to be in a time of 0.1 seconds. So induced EMF is, this is 0.75 minus 0.25 is 0.5 divided by 0.1, and that comes to 5 volt. So once you get 5 volt, you know the resistance of the coil. When an EMF of 5 volt is developed across a resistance of 10 ohm, current is simple Ohm's law, V by R, 5 by 10, that is 0.5 amperes. When current is 0.5 amperes, you know the question is what is the charge flowing in the circuit or the coil? I is equal to Q by T. That implies Q is to be found out, I is given to be 0.5. And remember, this is current. Current is always rate of flow of charges. That is the amount of charge flowing per second. So Q by, it is 1 second, because already we have divided it by 0.1 seconds here. So this current is per second. So Q itself is 0.5 coulomb. Option is C. Problem number 6. A coil of resistance 400 ohm is placed in a magnetic field. If the magnetic flux linked with the coil varies with time as given by the equation, then the current in the coil at time t equal 2 seconds is. Again, it is what you have to do is you have to get the help from Faraday's law, which gives you the induced EMF, and you know that induced EMF is rate of change of magnetic flux, so you can differentiate this with respect to time. Once you get the induced EMF, you know the resistance of the coil, and you can find out the current. So first of all, we will get E is equal to d phi by dt. That is equal to, differentiating this equation with respect to t, d by dt of 50t square plus 4, and induced EMF is equal to this is 100t plus 0, and at a time of 2 seconds, induced EMF is E of 2 is equal to t in, you substitute the value of t, then you will get 200 volt. So what is the current? Current I is equal to, from Ohm's law, V by R. V is 200 and the resistance is 400, and this is 1 by 2, which is nothing but 0.5 amperes. So option is A. Question number 7. The current in a coil changes from 4 ampere to 0 in 0.1 seconds. If the average EMF induced is 1 volt, the self-inductance of the coil is. Now we have to get an equation which connects induced EMF and the self-inductance and the rate of change of current. The easiest equation is E is equal to L di by dt. Again, I write only the magnitude. And induced EMF is given to be 1 volt. Self-inductance is the question to be answered. Di by dt is 4 ampere to 0, the change in current, minus 0 divided by time taken is 0.1 seconds. So this comes to L, self-inductance, is equal to 0.1 by 4, that is equal to 10 by 40, sorry, 1 by 40. I will multiply and divide by 10, 1 by 40. And you know that 1 by 4 is 0.25. 1 by 40 is, one more 0, 0.025, and this is in Henry, 0.025 Henry, and this can be written as 25 into 10 to the power minus 3 Henry, which is 25 millihenry. So option is B. Question number 8. A coil of area 0.025 meters square having 20 turns rotates uniformly at 600 rpm in a uniform magnetic field of strength 10 Tesla. The RMS value of EMF induced in the coil is nearly. Now, this is the principle of dynamo. A coil is made to move in a magnetic field, and the flux linked with the coil keeps on changing as the coil turns, and an EMF is induced, and that is actually the alternating current. And the induced EMF, we get the relation like this in a dynamo: E is equal to EM sine omega t. It is sinusoidally varying EMF, and after that this EM is obtained by actually substituting for NAB omega, where N is the number of turns in the coil, and the coil will be like this. It will be like this between the two pole pieces of a magnet. In the north and south poles of the magnet will be like this here, and now the flux passes through this, and as the coil turns, the flux linked with the coil keeps on changing. A is the area of the coil, and B is the strength of the magnetic field between the pole pieces. Omega is the angular speed with which it is turning, so that it gives the rate of change of flux. And this is the peak value of EMF induced, maximum value. Since it is sinusoidal, it keeps on varying. And now, if you want to get what is the RMS value, then ERMS, if you want to get, because the question is RMS value of EMF induced, the peak value, which is nothing but NAB omega divided by root 2. We know it. And ERMS is equal to number of turns in the coil is 20, and area of the coil is 0.025 meters square. Strength of the magnetic field is 10 Tesla, and omega angular rotation is 600 RPM, rotations per minute. So you have to convert it into omega. Omega is theta by t. You should turn it into theta by t. And theta is 600 rotations, means 600 into 2 pi. Every rotation makes 2 pi radians divided by, in a time of 1 minute, that is 60. So this gets cancelled. So this comes to 20 pi. So I can turn this into 20 pi omega angular velocity divided by root 2. Now the answer for this ERMS is equal to, you can multiply this. So what I will do is here, I have 3 zeros, one in 20, another is in 10, and another is in this 20. So these 3 zeros, I will sacrifice it for 0.025. So it becomes 2 into 25 into, this 0 I have removed, so only 1 is remaining, into 2 pi divided by root 2. And this will come to almost, this is 50, and this is into 200 pi divided by root 2. And better you know what is 1 by root 2. 1 by root 2 is 0.707. So this comes to 100 into 0.707, 1 by root 2 into 3.14. Now 0.70, if you multiply this 0.7 into 3, I will approximate it. I'll take this as I will donate 1 0 to this 0.707. So that comes to 10 into 7.07 into 3.14. Am I right? 1 0 from 100 is given to 0.707. So that comes to 7.07, and 10 will remain here. 10 into 7.07 into 3.14. So the answer will be, this will be, and if I take it as almost 7 and almost 3, 21 into 10, that comes to 210. And the nearest answer is 225 volt. And these types of approximations, you can do this so that you will get the nearest answer. And if you have your own method of solving these types of numericals, you can follow it. This is how I solve it. So the answer is 225 volt, option B. Question number 9. The magnitude of EMF induced in a coil is independent of resistance of the coil, change in magnetic flux in a given time interval during which magnetic flux changes by a certain amount, none of this. Now, induced EMF is a factor which depends on the change with respect to time. It doesn't depend on the resistance of the coil. Suppose the voltage across a coil depends on resistance, then it is because of Ohm's law. So that is because of DC current, not AC. So if you have a resistor and pass current through that, then you will get a voltage. And this is a direct voltage, and that depends on the resistance of the coil. Whereas if you have a coil and close the circuit by connecting it to a galvanometer and move the magnet towards the coil and away from the coil, then you know that this magnetic field produces a change in the flux and it induces an EMF across the coil. Electromagnetic induction, we call it so. Now, this induced EMF doesn't depend on the resistance of the coil. That arises only because of the change in the flux. And induced EMF will be depending on how fast is the flux changing. So it depends on these two, and it doesn't depend on A, resistance of the coil. Option A. Problem 10. A flat coil of 2 turns and area 0.1 square meter is placed vertically along east-west. The coil is turned through 180 degrees about a vertical axis. If Earth's horizontal field strength is 4 × 10⁻⁵ Tesla, the change in magnetic flux is. Now, magnetic flux linked to any coil can be written as flux phi is equal to NAB cos theta. The magnetic flux linked to a coil can be changed in many ways. Either you can change the number of turns in the coil, or you can change the area of the coil as we do in motional EMF. And you can change the strength of the magnetic field also, as if we have in Faraday's experiment where we take the magnet very close to the coil or away from the coil. That also changes the magnetic flux. And you can change theta also. That is what is found in this problem. This is the usual principle of dynamo, in which two magnetic pole pieces are kept and a coil is turning or rotating in between those two magnetic pole pieces. And when the coil turns, the magnetic field induced magnetic flux induced to the coil will be different, linked with the coil will be different, so that induces a current. Now, here the arrangement is like this. Now the coil turns by 180 degree. When the coil turns by 180 degree, what are the changes occurring? It is the theta which is changing. Neither number of turns change, nor area, or the magnetic field. They are all constants. Now let me realize it in a diagram. Let us take the coil as like this. This is one side of the coil, and this is another side of the coil, and the coil is rotating in a magnetic field, and the magnetic field is Earth's magnetic field. And you know that it is given the coil is placed vertically, and it is along east-west. So I will take this as east, and this as west, and this as north, and this is south. So the north-south is parallel to the ground. Suppose the north-south lies like this. The magnetic field it is like this. So this is the magnetic flux passing through the coil. Now once it turns through 180 degrees, its new position will be, the red side will be the other way, and the blue side will be towards the left. So the coil will be like this after turning through 180 degree. It will be like this, and the blue side will come to this side like this. So the coil has turned by 180 degree now. Now again, the flux passing through the coil will be normal like this. Now what is the change here? Suppose if I take theta 0 here, because normal to the coil and the magnetic field are in the same direction. So if I take theta 0 here, then theta will be 180 degree here, because the same normal comes out like this. Here the normal will be like this, and here the normal will be like this. So the angle will be 180 degree. So that is the change occurring when the coil turns from one phase to another phase. Now, if you want to find out the change in the flux, delta phi, I can write it simply like this: NAB cos theta 1 minus cos theta 2. So that is equal to delta phi is equal to N, number of turns in the coil, 2, area of the coil, 0.1 square meter, and the strength of the magnetic field is given 4 into 10 to the power minus 5 into cos 0 initial angle minus cos 180. Now delta phi, change in the magnetic flux, is equal to, here if you again substitute it into, then 4 into, I will take it as 10 to the power minus 6, because I have a 0.1 here, 10 to the power minus 1, 10 to the power minus 5, 10 to the power minus 6 totally. And this is cos 0, 1. And this is cos 180, minus 1. So 1 minus of minus 1, it is 2. So again I will get a 2. 2 2s are 4, 4 4s are 16, delta phi is equal to 16 into 10 to the power minus 6 Weber. Weber is the unit for magnetic flux. That is the change now. So option is D. Question number 11. A steady potential difference of 10 volt produces heat at a constant rate in a resistor. The peak value of alternating voltage, which will produce half of the heating effect in the same resistor, is. We know the definition of RMS, that RMS value of any AC, RMS value is always defined for AC, not for DC. RMS value of any AC is that equivalent value of DC, which produces the same heating effect as AC produced. So a steady voltage of 10 volt produces a heat, and that will be equal to the RMS value of AC. Suppose, so DC, VDC is equal to 10 volt. And if you want to equate these two, what is the equivalent value of this voltage in RMS, in AC? Then in AC, this is a RMS value, and that is 10 volt. So RMS value of 10 volt of AC and 10 volt steady DC both produce the same amount of heat energy. Now the question goes like this. The peak value of that alternating voltage, which will produce a half of the heating effect as this has produced. Now, what is the peak value of this AC now? So peak value of AC, Vm, is equal to 10 into root 2 volt, because we know that Vm by root 2 is equal to RMS value of AC. So the peak value of AC, this is again for AC, remember, this is AC value. Peak value of AC is 10 root 2. But their question is, they are not asking what is the peak value of the alternating voltage. They are asking you the peak value of that alternating voltage, which will produce half of the heating effect as produced earlier. So if you want half of the heating effect, you know, power developed in a resistor is equal to V squared by R. Now, if you want to have a power P dash, which is half of that produced earlier, then what you have to do with V? If you make V half, then the new power will be V squared by 4R, because you have to substitute V as V by 2. If you substitute V by 2, then power will be 1 by 4. So if you want power half, make V as V by root 2. Then P is equal to, and P dash is equal to V by root 2, new value of voltage, whole square, into 1 by R. So if you reduce the voltage to 1 by root 2 of the earlier value, then the power will be half of the previous case. So this is the power and this is the voltage which produces earlier power. Now if you want to know what is the voltage, peak value of that alternating voltage which produces half of the earlier power, then the new value of Vm dash should be equal to 10 root 2 by root 2, because reduce the voltage by root 2 and go for a power which is half of the previous case, because when you square it, it becomes V square by 2R. V square by 2R will be the half of the previous power. So that comes to 10 volt. So the peak value of that alternating voltage which produces half of the heating effect as earlier is 10 volt itself. Option is A. Question number 12. The reactance of a 25 microfarad capacitor connected to an AC of angular frequency 400 radians per second is. Of course, you can solve this problem yourself, and you can expect such type of easier questions in between also in entrance examinations. So we can't neglect it. Now the relationship between reactance, angular frequency, and capacitance, it goes like this. Reactance Xc is equal to 1 by omega C. Substituting the value, they are asking you the reactance itself, Xc is equal to 1 by omega is 400 into capacitance is 25 microfarad. And if you want to calculate this further, multiply 4 and 25. So Xc is equal to 1 divided by 4 and 25 when multiplied gives 100. So it will have 2 zeros. So again 2 zeros here. So this will be 1 and 4 zeros into 10 to the power minus 6. And this is 10 to the power 4, 10 to the power minus 6, 1 by 10 to the power minus 2. So X is equal to 100 because it comes to 10 to the power plus 2, 100, and this is ohm because it is reactance, and option is B. Question number 13. An AC source of 220 volt, 50 hertz is connected to a circuit having resistance of 80 ohm and inductive reactance 60 ohm in series. The current in the circuit is nearly. We work out such type of problems for theory examinations also, but here we are not given with calculators, but values are given in such a way that you can get the answer very easily. And if you want to know what is the current in an AC circuit, we know that the formula is I is equal to V by Z, that is equal to V by Z is here. So there is one resistance, 80 ohm, and there is a inductive reactance. There is only inductor, there is no capacitor in this circuit. And fortunately, the inductive reactance is directly given, not inductance. So you need not calculate XL. So root of R square plus XL square, which is directly given. So if I substitute those values, the voltage 220 is RMS, 220 divided by root of R square. R square is 60 square plus R square is 80 square plus 60 square XL, and current I is equal to 220 divided by 80 square is 6400 plus 3660 square, that is equal to 220 divided by, and this will be 10,000. 64 plus 36 will be 100, so you will have two more zeros, so 10,000, and square root will be 100. So 1 0 will cancel. 22 by 10 is 2.2 ampere, and the option is A. Question number 14. A resistor, an inductor, and a capacitor are connected in series to an AC supply of 220 volt 50 hertz. At resonance, the current in the circuit is 1 ampere. The power dissipation in the circuit is. Now, at resonance we know that the circuit becomes purely resistive. So if at all there is a power loss, then it is because of resistance only. Usually it is because of resistance only. Power is equal to, you can use the formula I squared R or V into I. But here what helps us is, this is voltage is given and current is given. So average power dissipated, you can calculate it like this. Power is equal to Vrms into IRMS into cos phi. That is what you do in AC circuit. But this is equal to 1 since it is at resonance. At resonance, the circuit is purely resistive and phi is 0, cos 0 is 1. Current will be in phase with the voltage. So power dissipated is equal to Vrms, that is 220, into IRMS, that is 1 ampere. So that is 220 watt. Only some theory knowledge is required here. Calculation is very simple. Option is B. Question number 15. In a series LCR circuit at resonance, the ammeter reads 1.5 ampere and the voltmeter reads 220 volt. The power consumed is, again, this is very similar to the previous question. At resonance means circuit is purely resistive and current will be in phase with the voltage, and power is equal to Vrms into IRMS into cos phi, and this will be again 1. But only the knowledge required is, here they have given ammeter reads 1.5 amperes and voltmeter reads 220 volt. Whether these values are RMS or not. Usually the current meters and the ammeters and the voltmeters, they read RMS values. They don't read peak values. So you can directly substitute these two values and get the power. So only that theory knowledge is enough to solve this problem. 220 into 1.5 and into 1, power factor is 1, and power is equal to, when you calculate this, this is 1.5. So make 220, half of 220. Half of 220 is 110. Add it to 220. Then it becomes 1.5. 220 plus 110, that comes to 330 watts, and that is option B. Question number 16. In an AC circuit, the instantaneous voltage is V is equal to 300 sine 100 pi t volts, and instantaneous current is I is equal to 4 sine 100 pi t plus pi by 3 amperes. The power dissipated in the circuit is. Now again, this formula goes the same. P is equal to Vrms IRMS into cos phi. Now this circuit is not at resonance. Current and voltage values are given in this sinusoidal form. If you just observe this, this is sine and this is sine, so no phase difference in terms of sine. But here we have an extra pi by 3 compared to this. So phase angle phi becomes pi by 3. This leads, actually, current leads, there is a plus pi by 3 compared to voltage. So this should be a capacitive circuit actually. Now, and these values 300, V is equal to Vm sine omega t. So this is the peak value of voltage, this is the peak value of current. So if you want to substitute for power, average power dissipated, Vrms is 300 by root 2, IRMS peak value of current by root 2, IRMS maximum value of current is 4 by root 2 into cos phi. Cos phi is cos pi by 3. and this comes to 300 into 4 by 2 into, this is cos 60, that is half, so 4 gets cancelled, so answer is 300 watt. Option is C. Question number 17. In a circuit having a coil connected to an AC source, the reactance of the coil is √3 times its resistance. Phase difference between the voltage across the coil and the current through the coil is. That is the question. You have to find out phase difference. Now, phase difference can be calculated using the equation cos phi is equal to R by Z. Now, here the given values are, the reactance of the coil is √3 times the resistance. Reactance of the coil, so given XL is equal to √3 times the resistance. And there is no capacitor in this equation. So we can write cos phi is equal to R divided by root of R square plus XL square. We will use this data. That is reactance of the inductor is √3 times the resistance. Then cos phi becomes equal to R divided by root of R square plus this one, √3 R whole square, that comes to 3R square. That is equal to R divided by, this is R square plus 3R square, 4R square. So root of 4R square. Root of 4R square is 2R. So the answer is 1 by 2. Cos phi is 1 by 2. So phi should be equal to pi by 3, 60 degrees. Option is A. Question number 18. The resonant frequency of a series LCR circuit is 800 Hz. If the value of resistance, inductance, and capacitance are double, then the resonant frequency will be. Now, the resonant frequency formula, omega is equal to 1 by root LC. It doesn't depend on resistance. So if resistance is doubled, halved, whatever you do with this, omega doesn't change. Omega naught doesn't change. But inductance and capacitance, their change will affect the resonant frequency. And it is said here, if the values of resistance, inductance, and capacitance all are double, so new value of omega naught dash is equal to 1 by root of, you have to substitute double the inductance, double the capacitance. So compared to the previous formula 1 by root LC, you will have a new appearance here, that is root of 1 by root of 4, that is half, which is, half is the extra term that you have got here, half of the original angular frequency. So omega naught dash is equal to 1 by 2 times the new, old value of omega naught. So old value of omega naught is 800. So the new value will be half of it, that is 400 Hz. Option is C. Question 19. A coil and a bulb are connected in series with an AC source. When a soft ion is introduced inside the coil, the brightness of the bulb will increase, decrease, reduce to 0, first decreases and then returns to normal value. Now, suppose you have a coil and a bulb. Coil plays the role of inductance and the bulb plays the role of resistance connected to an AC source. AC source will deliver its own voltage according to the instantaneous voltage. Now, you can replace this as L and R. Now the R core we have here, the current through this circuit is given by I is equal to V by Z. That is equal to V by root of R square plus XL square. Now this is the factor which is going to change here according to the problem. You know that XL is equal to 2 pi nu L. Of course, nu is not changed, only this factor is changed. Because as soon as you introduce an iron bar inside this, the core has changed, and that will increase the self-inductance of the coil. Because self-inductance is equal to mu n squared AL. That is a permeability of the medium inside the coil has increased because of the introduction of the iron rod. So the self-inductance increases and XL increases. When XL increases, you will have a more denominator and current decreases. So the bulb will glow with less intensity. So brightness of the bulb will decrease. Option is A. Question number 20. In the circuit shown, if the value of resistance is 60 ohm, then the current flowing through the condenser will be. Now, this is a problem, very easy problem, but provided you have enough amount of knowledge of the circuit, this is a style in which problem will be framed in entrance examinations. You will have to have a knowledge of the theory, and then you can easily solve the problem. Calculations needed here are very less. Now resistance is given as 60 ohm, so I'll write it as 60 ohm here itself. Now, can't you find out the current through this resistor? You can, because voltage is given, resistance is given. Simply apply Ohm's law, I equal to V by R. But the question is, what is the current through the condenser? Condenser is the other name for a capacitor. What's the current through the capacitor? But the simple logic here is resistance, inductance, and capacitance all are in series. When the components are connected in series, we are sure that current flowing through each component should be the same. Whether it is an AC or DC, current should be same. So what current flows through the resistor should be the current flowing through the capacitor. So find out the current through the resistor. I equal to V by R. V is 15 and R is 60 ohm. This comes to 1 by 4, which is nothing but 0.25 amperes. And the option is A. Problem 21. A transformer has a turns ratio of 200:1. If a cell of EMF 1.5 volt is connected across the primary coil, the output voltage across the secondary will be. Now, before going to the problem, what's a transformer? Transformer is a device consisting of a primary coil and a secondary coil and wound over an iron core. And if any alternating voltage is applied to the primary coil, that produces a varying magnetic flux which is linked to the secondary coil, and that induces an EMF here. But you will get induced EMF only when AC is applied to the primary coil. That produces a change in the magnetic flux. But here the given value is a cell of EMF 1.5 volt is applied. A cell of EMF 1.5 volt means it is a DC. DC passes through this coil and produces a steady magnetic field. That magnetic field doesn't change, and of course that magnetic field is linked to the coil, but there is no change in the flux. According to Faraday's law, there should be a change in the flux for EMF. If phi is a constant, then E is equal to 0. So no induced EMF will appear across the secondary coil. So the output voltage across the secondary will be 0, option D. Problem number 22. In a transformer, number of turns in the primary is 140 and that in the secondary are 280. If current in the primary is 4 ampere, then that in the secondary is, all are RMS values because nothing is told about the value, so it should be RMS. Now we have turns ratio formula for a transformer. It is the number of turns in the secondary to primary ratio, and also is equal to IP by IS. And also equal to Vs by Vp, but it is of no use here. They are asking you what is the current in the secondary. Current in the primary is given. Just substitute the values, we will get the answer. The number of turns in the primary is 140, which should come in the denominator. Number of turns in the secondary are 280, and IP current in the primary is 4 ampere. Current in the secondary is the question to be answered. So this will be 2 times, and current in the secondary will be 4 by 2, and that is equal to 2 ampere. Option 2, a direct problem with the direct substitution and answer. Easy problem. Question number 23. One conducting U tube can slide inside another as shown in the figure, maintaining electrical contacts between the tubes. As they are moved, electrical contact is not lost. The magnetic field B is perpendicular to the plane of the figure. Okay, if each tube moves towards the other at a constant speed v, then EMF induced in the circuit in terms of VLV, where L is the width of each tube will be. Of course, this goes in the form of or in accordance with the motional EMF. And here you see, well, the change that you have to do, we have already derived it that when a conductor moves over a frame like this, where magnetic field is applied perpendicular to the plane of the paper, as this moves, as the conductor moves, the area goes on changing. So the flux linked with the coil goes on changing. So that induces an EMF which is equal to BLV. But here we need to concentrate is, so this is a JEE mains question, you see, but still it is a very easy question. So already I have told that such easier questions will be asked in between. So you must be very careful in selecting such easy questions. Now, here the only difference is each tube moves towards each other at a constant speed v. So when one tube moves inside, the other one also will be moving inside. So if this tube moves through a distance x, then this also moves through a distance x. So total difference in the distance will be x plus x, that is 2x. So when you calculate the velocity v, then this is the only factor which is going to change in this formula. So v will be dx by dt when x changes by a factor 2x, that means double, then v changes by a factor 2. So totally the induced EMF in this case will be BL into 2V, because velocity will be double that as when a single rod moves. Here both of them are moving, so the area goes on decreasing. That induces an EMF which is the double the velocity I have to substitute. So E is equal to 2BLV. So option is C. Very easy problem, but remember this is as per JEE. Problem number 24. Current I in an inductor varies with time t as per the graph shown below. Below in means this is the graph. Which one of the following graphs show the variation of voltage in the coil? Now, the current variation is shown like this, I, and time is here. It is, you see, the current is increasing uniformly like this and decreasing uniformly like this. I'll extend this. Now, if you see the variation of current here, then it is the same everywhere. The change in current is same everywhere. The slope here, if you get the slope of the straight line here, if you get, it is everywhere same. And the change in the current is uniform everywhere. I'm not mentioning current is uniform. I'm saying change in the current is uniform. So according to the law, we have E is equal to minus L di by dt. The rate of change of current decides what is EMF. But rate of change of current is uniform here. How much current has changed from here to here? Same amount it has changed from here to here. So you should develop a constant induced EMF. So now if I draw the induced EMF here with the time, what happens at every moment here, then here is induced EMF. Then I will find that induced EMF here, when the current is increasing, I will write it as, since it is negative, I will put it here. And it should be a constant up to this, because the rate of change of current is uniform. However, inductance is uniform and it is a constant. Now, as the current starts falling down, again, the slope is same everywhere. How much current falls from here to here? The same amount falls from here to here. Again, di by dt is same. Now, the induced EMF is opposite to the initial EMF because it is a falling current. So, it should be again a constant EMF developed here. So, if I call this as plus V, then this will be minus V, same amount. And the graph resembles this one. So, this is the third option. Question number 25. In an LCR circuit at resonance, it is asked for Karnataka CET 2015. See how easy it is. The current and voltages are in phase, impedance is maximum, current is minimum, current leads the voltage by pi by 2. You know that a series resonance circuit at resonance will be purely resistive, and the effect of inductance and capacitance will get cancelled. and current in the circuit will be maximum, that is equal to V by R, because Z becomes equal to R, and the current is maximum, so this is wrong. And impedance will be minimum, so that when it is minimum it is R, so this will be wrong. And the current leads the voltage by pi by 2, no, it is purely resistive. Phase difference between current and voltage is 0, this is wrong. And the current and voltages are in phase because it is purely resistive, option A. How, see what type of easy theoretical question is asked.